are referred to as transshipment problems. So you might have a warehouse or a distribution center or a cross-docking station of some sort which accepts the supply from various supply points, and then it transfers them to the final demand points. So those are transshipment problems. You can again use a similar procedure to solve these problems as I've shown you before, and they can be formulated using linear programming as well. The main difference here, or one of the key things that you need to take into account here, is that the intermediate nodes, or your transshipment points as they're referred to, usually net out to 0. So everything that's coming in will eventually be equal to everything that's going out of these transshipment points. So the inflows are equal to the outflows in these problems. So this is an example of a transshipment problem depicted as a transportation graph. So I have two supply points here, 1 and 2. I have 3 transshipment points, 3, 4, and 5. And I have 2 demand points, 6 and 7. You are given the cost of transportation between these various supply, transshipment, and demand points. And you can solve this problem very similarly to a linear programming problem using just supply and demand points. The way you do this is by breaking the problem into 2 parts. Break the problem at the transshipment point and first look at the part where we're considering the supply points and the transshipment points, and then look at the part of the problem from the transshipment points to the demand points. So if you break the problem into 2 parts, it becomes a little more manageable to solve. If you were wondering how you would formulate this, again, the formulation, the expression is very similar to what I've shown you before. If you look at the objective function, however, we have broken down our objective function into 2 parts as well. So the first part is from your supply points to your transshipment points, and the second part is the cost of transportation from your transshipment points to your demand points. And you take the sum of those 2 values, and that is what you're trying to minimize. Also, your supply points will have a maximum. So for each origin, basically what you're saying is everything that is going into a particular transshipment point, everything that's going out of the transshipment point, that needs to be taken into account as well. And if you look at each transshipment point, the inflows minus the outflows should be equal to 0. So everything that's going into the transshipment point minus everything that's going out of the transshipment point should be equal to 0. So when you formulate the problem, you will have to have this one additional constraint in the problem itself. Otherwise, the other constraints are very similar to what we've seen before. So this is the example that I'm going to show you. We have 3 supply points in this case at Flint, Fresno, and Monterey. And you have 2 transshipment points at Santa Fe and Jefferson City. For your demand points, you have 2 demand points at Phoenix, Davenport, 3 demand points at Phoenix, Davenport, and Columbia. So those are the supply, demand, and transshipment points that you've been given. Again, if you look at how this grid is organized, it's split into 2 parts. The first part is from your supply points to your transshipment points, and the second part is from your transshipment points to your demand points. So this is what we're going to work with. I will show you this example in Excel, and I will post the solution online as well so you can follow it in your own time. Before we do that, I just wanted to bring up this second example as well. In this case, again, you have supply and demand points and transshipment points. You're given the cost of transportation per unit or per thousands of units, whatever the denomination might be. In this particular example, however, there are a few things to notice. First of all, you do have transshipment points. You do have these intermediate nodes that need to be taken into account. Also, these transshipment points have their own demand, which is possible. You may or may not see that situation occurring. Like I said in a previous scenario, you might have a warehouse where you're also catering to the needs of various customers. So these transshipment points might have their own demand. So Sacramento, for example, has a demand of 25. Chicago, for example, has a demand of 47. Sunnyvale, Dublin, and Bangkok are your three supply points, and they just have outflows possible for 45, 120, and 95. So in this scenario, you do have transshipment points with their own demands, and you have demand points with their own demands as well. So that's one thing which is different about this problem. Also, if you add up the total supply and the total demand, in this example, the total demand is more than the supply. So this is an unbalanced problem. So we will have a dummy node which we will use to supply to the various transshipment points and your demand points. So this is another transshipment example which is a little more advanced. However, for purposes of an example for the tutorial, I'll go back to the previous slide, and this is the example that I'll show you how to work through this using Excel. Okay, so let's go into Excel and try this problem. I've already formulated my basic data that I have from that problem. So I have two grids in this case. The first, or two parts to my overall transportation problem. The first part shows me the information from plants to various warehouses, and the other part shows me the information from warehouses to the retail stores. So I have the cost of transportation from plants to warehouses, cost of transportation from warehouses to retail stores. In terms of my constraints, I've been given the constraints for the plants in terms of their production, and I've been given the constraints for the demand at various retail stores. So that's the data I've already been provided with. As I've done in the previous example, I'm going to just copy the data into the model itself, and we'll formulate the model from that. So for the model itself, if you remember, we're going to use the exact same grids that we have in our problem, except instead of cost, we're going to have flows. So let me just change that in both of my parts. So you're going to have flows, and Excel is going to fill out this information for you. So let's shade them a little differently as well. We'll change them into red so that we know that these are cells which Excel will change for us. Also, rather than having the capacity and the demand requirements, we will have the outflows from the various plants and the inflows into the various demand points or our retail stores. Again, we will just get rid of the numbers that are already in those cells to have the outflows and inflows. We will have to formulate the outflows and inflows. So your outflows are just going to be the sum of that row, or the flows in that row. So what we're saying here is that we want to take the sum of everything that's coming out of Flint, the sum of everything that's coming out of Fresno and Monterey, and what you're doing for your demand points or your retail stores is you're taking the sum of everything that's going into Phoenix and some of everything that's going into Davenport and Columbia as well. So once Excel fills these cells for us, we will have the outflows for the plants and the inflows for the retail stores. However, in addition to just having outflows and inflows for your plants and retail stores, which are your supply points and demand points, we also have transshipment points in this case. So we need to have inflows and outflows from that transshipment point. So a transshipment point will have both inflows as well as outflows, and we want to make sure that we set a constraint where the inflows are going to be equal to the outflows. So let's do that as well. So go to the first grid and also have your inflows to the warehouses. And this will just simply be the sum of this column, which shows you everything that's going into Santa Fe. And similarly, everything that's going into Jefferson City. So you need to have the sum of that column for that warehouse. So these are your inflows into the warehouse. And you want to have the outflows from the warehouse as well. So we should have that. And you'll have the outflow from these various warehouses. So that is going to be in your second part of the grid. And that will simply be the sum of everything that's going out of those two warehouses as your outflow. So we need to do that for Santa Fe and Jefferson City, both of those. So now that you've specified your problem, so we can simply go into Solver now, but before we do that, we will have to also specify our objective function, which we haven't done yet. So let's do that. So our objective function in this case is going to be a combination of two things. It's going to be a combination of the flows and cost between the plants and the warehouse, and secondly, the flows and cost between the warehouses and the retail stores. So let's formulate that in two parts. So the first part is going to be cost of transportation from plants to warehouses. And the second part is going to be the cost of transportation from warehouses to retail stores. And again, just as we've done in the past, we will just take the sum product of the flows and cost. So in this case, it's going to be the sum product of my flows between plants and warehouses and the cost between plants and warehouses. And the second component of my cost equation is going to be the sum product of my flows between warehouses and retail stores and the cost between warehouses and retail stores. So those are your two components to the cost, and your total cost then is simply going to be the sum of these two components to your cost. So let's format these cells to be currency cells, and we want Solver to minimize our total cost for us. So let's just format that. And now we're ready to solve this using the Solver tool. So let's go into Solver. Again, go in the data menu under Solver. Let me just reset everything here. So what I want to do is set the target cell to be equal to the total cost. I want to minimize this. Also, I want to have two sets of changing cells in this case. So there are two sets of cells which are shaded in red here, which I want to change. So I will choose the first set, and I'll hold the control key and also select the second array of cells that I want to change. So Excel Solver will take into consideration that these are two sets of cells that I'm changing. For my constraints, first I will put in my normal constraints where the outflows from my plants have to be lesser than or equal to the production. They have to be lesser than, the outflow from the plants has to be lesser than or equal to the production capacity of those plants. That is your normal constraint. The second normal constraint that we've had before is that your inflow into the retail stores has to be equal to the demand requirements for those retail stores. That still holds. The last constraint, which is new in this case because of the transshipment problem, is that the inflows into your warehouses, which are these two cells here, have to be equal to the outflows from your warehouses, which is these two cells over here. So you have to add that additional constraint in this case. So we have three sets of constraints now. Go under options and again make sure that assume linear and assume non-negative are checked, and you can now solve the problem. So what we have in our solution then is that it's going to cost us $12.85. We will be able to satisfy the demand at the retail stores. It was 35, 30, and 35. And we've exhausted all of our supply from the various plants. 43, 26, and 31 are the capacities that were given to us, and the outflows from those plants are equal to those exact numbers. So we've been able to solve this problem using one additional constraint where the inflows into the warehouses are equal to the outflows from the warehouses. The other two sets of constraints where your demand has to be satisfied and your supply from the various plants